Hello, this is Jonathan with Robotics, presenting another episode of ROBOTIS Talks. And today, I'll be speaking with Professor Heather Culbertson from the HaRVI Lab at USC.
Thank you so much for the introduction, Jonathan. I'm really excited to be here.
Would you like to start off by giving our listeners a little bit of information about what it is you guys do at the HaRVI Lab?
Of course. So I am the director of the HaRVI Lab, which is the Haptics, Robotics, and Virtual Interaction Lab. So we are in the Department of Computer Science at the University of Southern California, and we handle everything to do with the sense of touch. So we study how humans interact with our world and technology through touch, as well as how robots use their sense of touch to kind of perceive the world around them.
Oh, that's a really interesting field of study. Would you be able to share a little bit about what inspired you to sort of travel down this path?
Yes, so I really got into robotics when I was an undergraduate. So I'm in computer science now. My undergraduate degree is actually in mechanical engineering, and I got really into robotics in our mechanical engineering first year design class, where we were designing with the Lego NXTs. And so that got me really, really interested in robots and building things. And so I knew that after that class, I knew that I really, really wanted to work with robots for my career. But as you know, robotics is a really big, diverse field. So
Yeah,
there's a lot of
there's
different areas. And so I spent a lot of time trying to figure out what within robotics is my passion. And so then I came to realize that it's actually working with robotics and people, the interaction of how people interface with robotics and technology that really excited me.
Yeah, I noticed when going through a little bit of your past research that there's a lot specifically about the emotional interactions of touch and robotics, more than I would have expected. I know recently you've been working on some research about the contextual grounding for like haptics feedback and things like that, and what the environment people experience these interactions in actually affects their interpretation of them. But you've done a lot of research about the emotional impact of the touch and robotics space.
Yes, yes, we absolutely. So, a large area of my research, my lab, has been on this social touch. And so, this is work that I started when I was a postdoc up at Stanford, working with Allison Okamura, looking at the area of social touch, which is studying how people interact with one another through touch. And so, specifically in the field of social touch, we talk about our interactions with touch, looking at hugs and high fives and handshakes and a pat on the back. But our social touch interactions are so much more nuanced than that. It's not just the physical interaction, it's not just the mechanical parts of the interaction, but what is actually being conveyed during the interaction. So, is a hug going to be a loving hug, or is it a sympathetic hug? Is it a comforting hug? So that's what we're trying to understand in our research, is not only trying to replicate the social touch, but trying to understand the intentions behind the touch so that we can create this sort of virtual communication. Because I started this work well before the pandemic, but obviously it became a lot more prevalent and a lot more, I don't want to say useful, but
The
more in
whole
kind of
world changed to
limelight.
really value what you're doing.
Yes, correct. Yeah, understanding the importance of social touch, because during the pandemic, obviously, we all lost that social touch. We were having to be completely removed from one another. And so we all experienced what's called touch starvation, which is experiences of loneliness and depression and isolation that you get from not being able to experience that levels of touch from one another. And so that's what we're trying to do within our research, is to understand what are these components of the actual social touch, the social physical communication between two individuals, so that we can kind of augment these communications and help people communicate, say, across a distance to their partner who is, their mother who lives across the country, or their partner, who example, who is traveling, or for someone who example, someone who's in the hospital who can't receive that social touch or may be isolated by living in a nursing home.
Oh, that's interesting. I wonder what kind of effect have you been able to conduct a study on how that sort of mediated social touch compares to real in-person social touch? Is that something that you guys have been able to research into directly?
We have been studying right now, not the effects of the social touch. So, not looking at, for example, how well it does at eliciting emotions the same way that physical social touch does. So, we have not been looking at it from the standpoint of how well does it work in terms of calming someone down or reducing anxiety. But we are, with the approach that we are taking right now, is to see how well does our virtual touch compare to direct human touch in terms of conveying information. So can we convey, for example, that the virtual social touch is loving or happy or sympathetic or sad? Can we still convey that same information across that distance? And what is it about that virtual touch that conveys that information?
Oh, that's interesting. I know that in one of your recent papers, the mediated social touch, one of the things you were also looking at, sort of in the background, is the different modalities of touch and how those might impact people's reception of that touch sensitivity. Is that something that's been interesting to you? Like, have you seen any interesting results from that specific research?
Absolutely. So when we are trying to take from real social touch and putting it into something that's mediated, like a virtual social touch, we have to very, very much compress it down. So if you think about social touch between two individuals, it's a very, very complex interaction because you have forces, you have temperature, you have slip, you have um, large area of contacts. And when we're creating these haptic devices, we're creating like these wearable haptic devices to try to convey that same information. But it has to be so much compressed down. So it has to be really, really, really compressed down to try to get into that wearable format. So what you are talking about is the work in the different modalities that we've been studying to see what is that type of modality that we should understand or we should actually be creating in the types of actuators. So, should we be focusing on the thermal information? Should we be focusing on the pressure information? Should we be focusing on the skin slip information? Should we can we do it as vibration, for example, something that still might convey the same sort of spatial temporal signals, same sort of spatial temporal patterns as the original social touch does, but is not realistic at all, does not feel anywhere close to that original social touch. And so that's what we're trying to understand here, because the closer that we want to get to creating the realism of the original touch, the larger and more complex our system is going to be, and the harder it's going to get actually to be in the home.
I can imagine that this is an amazing engineering challenge, harkening back to sort of your background in mechanical design, trying to figure out how best to replicate all of these different motions in a way that's both has a high amount of verisimilitude as well as I'm sure safety is a major concern since these are things that are literally being pressed into people's skins, as well as I'm sure that you've done some research into the materials of how best to replicate human skin as far as the tactile sensation and things like that.
Absolutely, absolutely. So yeah, we've been studying how realistic do we need to get it. Do we want these virtual social touches to be? Do is there a certain point where it's too realistic, where we're getting into kind of a haptic uncanny valley, where it would be then too weird or too unusual that a person would not want this level of realism in these virtual social touches. And
You,
so you're right. All of these haptic challenges are very much hardware focused. And so what we're actually trying, what we are actually have learned in these in this analysis is that the modality of touch that we use in our wearable format does not matter. In the modalities that we have tested, the modality does not matter in terms of conveying that information. So we're still able to convey the same information. And when we talk about information for emotions, we're talking about valence and arousal. So valence is whether the touch is positive or negative, and arousal is how strong the conveyed emotion is. So regardless of what type of modality that we're actually using, we for that mediated social touch, we're still able to convey that same information. So our results show that it likely doesn't matter what is the modality that we're using to convey that virtual social touch. Users obviously are going to have different preferences on what they prefer from a comfort level. But in terms of conveying that information, the modality does not seem to matter as much as we had originally thought that it would.
Oh. To sort of continue the conversation in the direction of the mechanical design of these things, I'm wondering what specifically you mentioned comfort, and I brought up safety earlier. What does the process of designing these things look like, especially with consideration to these are devices that must be applied directly to the human body? So, comfort and safety are huge factors, as well as verisimilitude and other performance concerns.
Absolutely. So, all of our systems are arrays of actuators because we want large scale area coverage. So, first of all, I'll talk briefly that about why we are covering the forearm. So, all of our devices are covering the forearm area here. The reason we have chosen the forearm coverage is because this is one of the most acceptable areas of social touch across a large portion of um, different relationships between users. Yeah, so if you so like for example, it's appropriate for your friends to touch your forearm or your family members or even like even like an acquaintance, for example. This would be an appropriate location. So we wanted something that it where a location on the body where first of all it's easy for us to mount actuators to, and it is comfortable and appropriate for social touch. So the three locations that are most appropriate are the hand, the forearm, and the shoulder. So the shoulder is very difficult to mount to, so that's why we did not choose the shoulder to attach for social touch. The hand, we did not want to occlude the hand, so we did not want to prevent the user from being able to do other tasks. So that's why we went with the forearm there, because this gives us a very large canvas of area to work with. Once we decided then we wanted to work with the forearm, we have a large area that we want to cover. So we have a large area, and when I'm like touching the forearm and I'm kind of stroking the forearm or squeezing or patting, I have like one contact point, which is my hand, which is moving. But when I want to create this in a wearable format, that would be very challenging if I have one object that is moving across the arm. Like you think of like a robot arm or a single servo that's going to be moving. That's very, very difficult. It's going to be big and bulky. It's too big and bulky. So that's why we have arrays of much smaller actuators.
Yeah, and you've developed a few different modalities of touch, skin slip, just straight indentation, all of these things.
Yes.
Yeah.
Yes. So now that we knew we wanted to do we want to do arrays of actuators on the forearm, then we wanted to look at okay, what's the best we can do with existing actuators, because we do work with hardware, but we are computer scientists at heart. So we're not going to be creating novel actuators within our lab. So we use off the shelf. We use off the shelf actuators where we can. So the first system we created was with normal indentation, so things that are moving in and out of the arm. And so we use these voice coil actuators, so like these mini speakers that are just going to be moving a couple of millimeters in and out of the arm. Then we are also looking at skin slip, and this is using the Dynamixel
Yeah,
Dynamixel.
XL330, I believe.
Yes. That's correct. And so those are great because we can very, very accurately control the position and the speed at which those rotate along the arm, along the top of the arm. And so, and we've also looked at vibration, and we've compared those three different modalities, and have showed that in terms of comfort, the system actually with the slipping with the Dynamixel is actually the highest comfort system at the highest level for comfort for the system. But in terms of conveying the different information, it's actually equivalent across the three different devices.
That's interesting. I wonder if I know the sort of or the indentation device. It sort of wraps around, if I remember correctly. It's almost like a glove for the forearm. I wonder if that attachment method has an impact on the comfort level.
So it definitely could have an impact on the comfort level as well. So the vibration, so that system is actually being used for both normal indentation and vibration. So the actuators that we chose, because they're voice coils, they can be driven at high frequencies or low frequencies. So at high frequencies, they output vibration, and at low frequencies, they output normal indentation. So it's actually the same system for both. But I actually believe that it could be more due to the modality rather than the system itself. So, but that could be something that we could test is if the user, because you're right with the slipping system that we had tested, the user just rests their arm on top of the actuators. It's more of a platform that the user rests their arm on. So that's something that we could test to see if we rest their arm on the normal indentation actuators, whether that improves comfort or not.
And then you've also mentioned that for the design of these, they're all arrays of actuators. I would
Yeah.
imagine that the coordination to create these very lifelike movements is a difficult programming and sort of orchestration issue. What does that look like on your guys' lab side? What does the process of developing these motions look like?
Uh, Very great question. So, absolutely, the algorithmic side to get realistic feeling motions and coordination between the different actuators is a very challenging problem. So, we take a data driven approach to all of our algorithms here. So, we actually record pressure data from real social touches. So we have arrays of pressure sensors that we record real social touches. So we have two different data sets, one that is recorded from what we call gesture based data, which is distinct gestures, which are strokes, pokes, pats, squeezes, taps, and massages. And then we record what those arrays of pressure sensors, kind of the data looks like. Then we also have emotion based data, which is when we ask users to convey a specific emotion to their partner and we record it. So this would be something like happiness, sadness, sympathy, attention, gratitude. So we also have a data set that is emotion based, but both are recorded arrays of pressure sensor data. So it's a spatial temporal pressure data that is then mapped to the output of the actuators.
Yeah, and
So the way in which we do this mapping, regardless of whether it's going from gesture or whether it's going from an emotion, it's still spatial temporal pressure data. So we first look to find where is the initial point of contact onto the sensor, and then you track that point of contact. So basically, you're tracking the point of contact because we're assuming that is the user's hand as they touch the pressure sensors. Then you track that point of contact, and that is the moving point of contact that is then going to slide up and down the actuators.
oh, and then I would imagine that there's also a bit of sort of design challenges in making sure that these touches can be recreated accurately among the three modalities of touch that you guys are focusing on. Is that something that's as difficult a challenge as I would imagine it is?
Yes, absolutely. So the first one that we did, the first mapping algorithm that we did was from the data to the normal indentation voice coil device. So that's the first one that we created where we mapped the pressure to the indentation level. So we mapped the recorded pressure to the indentation level because the higher the pressure, the more the person is like pressing into the arm. And so the higher level that the voice coil should be pressing, indenting down into the arm.
And I would imagine that normalizes pretty well. So,
It normalizes pretty well. It is still open loop control with the voice coils because they're we are not actually directly sensing the motion, but it is pretty good. It is pretty good control. It is pretty good relationship. So once we got that working, then we mapped it to the vibration. So then we were able to map it to vibration. So instead of doing the pressure to indentation level, we did pressure to the amplitude of the vibration. So
so
you
higher
still have
frequency
like an
vibrations.
underlying signal of vibration like 100 hertz, and then you change the amplitude of that vibration the same way.
Okay.
And then to get to the slip device, you we changed the pressure signals to rotation because as the device basically, I'll see if I can show it on my arm, as the device rotates, it's going to press more or less into the skin. Okay, so as the device rotates, it's going to press more or less into the skin. So the higher the rotation as it gets closer to 90 degrees is going to be pressing more into the skin. So then we are able to do a mapping from the pressure level to the rotation of those servos. And so that's how we get from the same pressure signals, from the same mapped pressure signals to the rotation of that servo device.
Okay, that's quite an interesting process. I know you've done a lot of research in this space with your lab. Would you mind sharing a little bit about what your favorite thing that you've discovered or worked on is so far?
All right. So so Jonathan, I'm having trouble choosing. I can't choose a favorite project. That's like choosing a favorite child. Um,
Fair enough.
But I will say that I'm having so much fun with one of our brand new projects, or relatively new projects in our lab, in which we're creating a fully immersive VR surfing simulator, which is using a 6 degree of freedom motion platform to allow you to be fully immersed into a surfing environment. So in this work, we are studying pain management for chronic overlapping pain conditions with surf therapy. So this is in collaboration with Jason Kutch and James Finley from the Health Sciences campus at the Keck School of Medicine within USC, and they are studying the effects of actual surfing therapy on the ocean in the water on chronic overlapping pain conditions. And we want to see if we can get the same results in virtual reality. So it's a 6 degree freedom motion platform, kind of similar to what you see in a theme park. And we have a surfboard on it. So we put this giant surfboard on it, and you can, and you were integrated with an Oculus headset. You can paddle around, you can ride a wave, you can kayak, you can paddleboard with it. You have full control over it. The one thing we don't have integrated with it yet is force sensors to really allow you to shred the wave.
That's quite
But
cool.
we're working on it.
Have you started to see any of the results from that research? Do you have any early indications of how the therapy is working in this virtual environment?
Are just starting to do the we're just starting to do the test now. So unfortunately, we do have results in terms of the immersiveness and simulator sickness, which people do not get sick using our device, even though they're in virtual reality. But we do not have results yet on the effectiveness of our system with pain management.
I'll be sure to
But
include
stay
the
tuned.
links to the results. Yeah, once that's available. Uh, but before we head out for the afternoon, is there anything else you'd like to share with any of our listeners?
Jonathan, when we've been talking so far right now just about the sense of touch, but I really want to just mention that my lab really is also looking at the multi-sensory integration. So, because our senses do not exist in a vacuum, so everything we see, everything we feel, everything we hear, all of this is affecting our total interactions. So, to get us really, really immersed in our interactions, we really need to understand all of our senses. So, in addition to touch, in some of our projects, we're also looking at vision and sound as well.
Oh, that's very interesting. I can imagine that pairing all of these different modalities of interaction makes a huge difference as far as the conveyance of these social aspects you're talking about.
Absolutely, yes. It really does. It really does make a huge impact in not just what the user is experiencing, as well as the overall interaction and the acceptance of the technology, because you never really you're never going to get this like disembodied interaction that's totally out of context. So we really need to so the next that's really the next thing that we're going to push towards on in our research is understanding how the social touch works in the context of the interactions of in the context of virtual interactions with another person.
Okay, that makes a lot of sense. And I would love to see where this research goes in the future. I'll be keeping my eyes peeled. Uh,
Great. Thank you,
so,
Jonathan.
for any of our listeners who want more information about your research or to read any of your papers or anything like that, where would they be able to find more information?
So I definitely recommend that you check out our website.
Okay. And I'll be sure to include that in the video description, as well as a link to the research specifically on social touch. Uh, we have a companion video powered by Dynamixel going into a little bit more detail, talking about the effective contextual grounding on social mediated touch as presented by your lab.
Great. Great. Thank you so much, Jonathan.
This has been another episode of ROBOTIS Talks featuring Professor Heather Culbertson from the USC Department of Computer Science for their HaRVI Lab.